so it is working. Let me just double check the audio part, make sure it's recording the audio part as well. Yep, looks like it's working. All right. Okay, so today's lecture is going to be important because I'm going to show you guys how to use a tool called LogiSim. It's for logic circuit simulation. And what we'll do is to make our own circuit for adding. Your homework assignment is to make a circuit for subtracting. So I'm going to show you something that you have to borrow in order to get your homework assignment done. So let's go ahead and get started. I think this is a really great tool. I just found it yesterday, so that's why it's new to me as well. There we go. All right. So let's go back here. I put up 2 additional links already. One link is for the homework assignment, and the other link is for the tool that you need in order to do your homework assignment. This is the home page that I was referring to, and the tool is pretty easy to use. I have used a lot of tools similar to something like this to design circuits and do simulation and stuff like that. And this is by far the most intuitive tool that I have come across that has this type of ability. A lot of tools for designing circuits and whatnot, they have a completely different type of user interface than most of the other types of software. But this one is easy to use. It's just a Java jar file. So as long as your computer has Java installed, it doesn't even have to be a more recent version of that. It will run. So I'm going to show you. I'm just downloading the file. It's just one little jar file. And to run the program in Windows, I think you can just double click on the jar file and it will run it automatically. In Linux, it is actually the same thing. I can go to my downloads folder and just double click on the jar file, and that should run it automatically right there. Okay. So it's a really kind of nifty little tool. So what I'll do is I'm going to design a half adder and then make a component out of it, and then use half adders to make a full adder, and then make a component out of that, and then I'll make a 4-bit adder. Your job is to make a subtractor, okay, a 4-bit subtractor. So what I'm doing in this class is going to be pretty much the same thing that you have to do in order to get your homework done. I'm not going to make this file available, because if I make this file available, all you have to do is to go in and change a few gates and it's done. Okay, which kind of defeats the whole purpose of trying to get you guys to get familiarized with a tool like this. For those of you who are pursuing a degree in computer engineering or electrical engineering, this is something that you really need to get used to anyway. Okay, because that's how. But this is actually a really easy tool to use compared to some of the other tools in industry. All right, so I'll just go ahead and maximize this screen here. Unfortunately, it doesn't have an ability to zoom as far as I can see. It can maximize the screen, but it doesn't zoom in. So that's kind of like a limitation, like a bummer. Okay, so what I'll do is I'm going to design a half adder first. Okay, now if you still remember what a half adder is, it performs the basic rule of adding. So I'll go to I'm going to use a editor, kind of like a little whiteboard notepad thing here. And what I'll do is I'm going to show you, something that you should know already because we talked about it just 2 days ago. But I'm going to put it here just so that we get that part. Okay. So the part that you need to know is 0 plus 0 has a result of 0, and the carry is 0 as well. 1 plus 0 is 1 with no carry, or the carry isn't 0. All of this stuff is getting recorded, so there's no need to copy what I have on the projector now. But if you see something or think of something that is not on the whiteboard or projector, that is something that you might want to write down. Okay, so these 4 rules for adding, for binary adding, is something that we talked about on the other day already, except I drew a picture on the whiteboard. Some of you took a picture. So what we'll do today, the first thing we'll do is to capture that design in this tool, okay? But this tool is more than just a tool for documenting stuff or to capture a design. It is also a simulator, which means once we capture it, we can actually run the circuit, and you can actually see how two numbers are added using those circuits. So with this in mind, we're going to go back and say, okay, what is the carry flag? The carry flag is really just the conjunction of the two input bits. So if I label this input bit as X, this input bit as Y, then the carry is X and Y. I can use an AND gate to calculate the carry. So this is the easy one for adding. For subtracting, the rule is a little bit different. Okay? And then the result, and this is the result column here. The result, there are several ways to express it, but most people express it this way. It is not X and Y, or X and not Y. Okay, we talked about this the other day as well. How the result, if you do it this way, it will give you the right bit patterns. Okay, it will give you back 0, 1, 1, 0 corresponding to the patterns of X and Y, like the way it is described in the on the projector. Are there any questions about this? This is kind of like a quick warm up of what we talked about the other day on Tuesday. So what we want to do, the first thing we want to do is to design the circuit for this. Okay, it already has gates, already, so we can pull out these gates here. Now, when you pull out a gate, you can also change the number of input. The default, for whatever reason, is 5. We don't need 5 inputs for our AND gate, so you can change it to a 2. And the gate size is by default a medium size, which is pretty big. We don't want to use up all that space, so we can switch it to narrow. Facing east means the output gate is facing east. We want it to be kind of more designed vertically, so we can change it and make it face south like that. So now we have a little AND gate here, and I'll just stash it right here. Okay. So when you see an AND gate, it's really hard to see from your perspective, but when you review the notes on YouTube, you can pause it and you can zoom in. There are 2 little dots to the north. Those are the input ports, and then there's 1 dot to the south, which is the output port. Okay, so that's what you need to do to make the connection. So I'm going to pull all the gates out first. Okay, I need 2 more AND gates and an OR gate. And with the OR gate, it is the same way. I'm going to have to change the orientation so that it faces south. Change the size of the gate to narrow. Change the number of input to 2. And that's about all I need to do. So I'm going to put the OR gate down here. Yes, go ahead.
If you were to use 5 inputs, or you had 5 inputs set up and you only use 2, would the other ones automatically be defaulted to 0?
No, because they're basically just floating, and you don't want any input gate to be floating, because that means the voltage is undetermined. So you definitely want to change the input to only 2 inputs. Whether you change the size or not is entirely up to you, but I don't like to waste a lot of space on these symbols. Okay.
Thank you.
Sure. We also need 2 NOT gates, or because we need the NOT gates for the result. So the NOT gate is here, and we can turn the gate size to narrow. It by default, because it's a negation, it only has 1 input and 1 output. So we gotta draw that here. Oh, we need to change the orientation so it faces south as well. So I'm gonna put 1 here, and I'll put another one over here. All right, so I have all the major components already for a half adder at this point. Okay, so the next thing we have to do is to just arrange everything so that it has 2 input pins and 2 output pins. So I'm going to move things around a little bit. All I did was to drag, and I dragged the mouse to create a rectangle to select everything, and then you can move all of these items on the screen anywhere you want. Okay, that part is pretty standard. So now what we also need are 2 things from wiring. So when you click on wiring, it shows you all the quote-unquote terminal stuff. What we need are 4 pins at this point. Now the pins are kind of the same thing, they have an orientation. So for the input pins, I want them to face south. Okay. And output is no here, which is good. 3-state, let's specify no, okay, because we are not dealing with tri-state type of pins, so we will specify no for 3-state, and I think that should be it. Oh, you can also specify labels, okay? So the label is kind of useful because it puts the label right next to the pin, so you know which pin is which pin, in the design. So in this case, I have 2 inputs, so I'll just label this one as X. The label itself has its own location. In other words, is it to the northeast, southwest of the pin itself? So you can choose. We can always change these later, so I'm not too concerned about that. Okay, so here's pin X, and I'll need another pin, and we'll call it Y. So now we have another pin, and you can always change the settings after you create a pin. So if you forget to set something before, it's no big deal. You can always change it later. So now we have 2 pins for input, and we'll need 2 pins for output. So for output, I want the pin to be facing north because that's where the oops, I forgot to click here first, because if you have one thing that's already selected, it would change the property of that one. Okay, so now that I have clicked, something here, in other words, I'm creating a new pin. I will make this pin face north. So the terminal or the connection point of that pin is facing north. It just makes everything easier to connect. And this is, in fact, an output pin. It is not a 3-state pin. We do not have to specify pull behavior. It's like a little bit beyond what we have to talk about in this class. And this is for my result, so I'll label this pin R. And I'll just dash it down here. This is the result pin. And I need another one. So let's go to pin here. And I'll change the name to C, which is our carry pin. And the carry pin is going to be close to here. I can always rearrange things a little bit. All right, so now we have every pin and all the components that we need. Now we just need to draw connections between all of those components. Depending on how compact you want the design to be, you can always kind of squish everything together. But for this class, for just illustration purposes, I don't need it to be too compact. So I'm going to leave it the way it is right now. For the input pin, one has to go through the negation on each one of these AND gates. Let me just kind of pop up this box here and make it smaller so that I can actually fit both the design and the text on the same screen, so you can basically look at the text representation versus the graphical representation. The labeling is the same, okay? So we have X, Y as input pins. We are trying to calculate the sum of X and Y as R, and then we also want to determine, do we have a carry of 0 or do we have a carry of 1 to the next digit, okay? When you look at the AND operation here, this AND operation is implemented by this AND gate here. This OR gate is this OR gate here. This AND is going to be this AND. This AND is going to be this AND. This NOT is going to be this NOT gate. And this NOT is going to be that NOT gate. Are we doing okay so far as mapping the text representation of the expressions to the graphical representation using gates? Okay, so there's nothing really new to the graphical representation, except when we can actually run the simulation using the graphical representation. Okay. All right. So now we just have to draw some connections between all those pins. So I'm going to focus on this screen here. It's difficult for you to see because I cannot zoom in any more than. I suppose I don't have to zoom in. I can change the resolution of the screen so you can see better. I'm not sure how well that would work. Okay, but when you put your mouse pointer and hover it over the connection point, it changes its right there. Do you see the highlight? It puts a little kind of neon green circle on top of the one little dot that is supposed to be the connection point. Okay, so at this point you can click the mouse, hold down the left button, and then draw a line, okay, to wherever it needs to go. So in this case, I wanted to go to the left side of the AND gate right below that. So I'm going to stop here and then drag another line and then finish the connection here. Is that okay so far? Okay. This pin also needs to connect to here as well as here. So I'm going to finish pin X first, and then I'll deal with pin Y. So once again, you can actually tap it from the middle of a wire and make the connection like this. And I'm going to make another tap here so that I can finish pin X all together. So are there any questions about what I have just done? How to make connections between the components? It's just dragging your mouse, and it automatically makes right angle turns. If the right angle turn, orientation is not what you want, you can always, stop and then drag it again to force it to basically make a right angle turn in the right orientation.
I have a question.
Yeah, go ahead.
Can you do diagonal?
No, it doesn't do diagonal. Yeah, most schematic capture programs do not do diagonal, they only do right angles. Yep. It's only when you actually design a PCB, a printed circuit board, then making diagonals makes a difference. Yep. This is just specifying the logical connection. It's not actually how the circuit is going to be connected. So one thing you might want to notice is there's a bubble here, okay, and there's also a bubble here. It means it is actually connected. Now I want to connect Y to the pins that Y is supposed to connect to. Now you can see that Y, this wire is crossing the other wire, but you don't see a bubble here. That means they're not connected. One is going over the other one with no actual electrical connection. But now I can make pin Y connect to this negation here and go over to the non-negated side of the AND gate here, and then go over to this AND gate over here. And then the output of this NOT gate goes to the input of this AND gate. So I'm basically halfway done already at this point. This output from this AND gate goes into the input of this OR gate, and this one goes to the other side of the input of the OR gate. The output of the OR gate is just going to a pin, and then the output of this AND gate is just going to this pin here. I did not align it correctly the first time, so I'm going to fix that. All right, so now that everything is connected, I can actually drag it around, because once the connection is made and you change the location of the component, the wire will follow accordingly, which is kind of neat. All right, so I have a half adder already specified here. Before I turn this into a component, because I don't want to have to copy and paste these things like 8 times for a half adder. So what I'll do instead is to test this first. If this works out, I'm going to turn it into a component. Once you turn it into a component, you can make instances of that component. Okay, so it's kind of like I'm creating a struct in C++ programming. Okay, once I have a struct, I can have either instances of that struct itself, or I can put that struct into another struct for for hierarchical design. All right, so I'm going to test this. Now it is actually being tested already. If you kind of notice what is inside the bubble, it's kind of hard to see, but there's a 0 here, there's a 0 here, a 0 here, and a 0 here. In other words, the circuit is actually being simulated as we designed the circuit. Okay, so this is basically 0 plus 0 has a result of 0 and no carry. Makes sense, right? So we want to test all of the other cases. In order to test for the other cases, you have to switch the tool from the edit selection tool to the simulation tool or change value tool within the circuit. So with that tool, you can click on an input pin and it will alter the state. It will just kind of toggle the state of an input pin. So now I have 1 plus 0. Do you guys see how the green wire become kind of like brighter? Because when it's bright, it is a 1. When it's dark, it is a 0. Okay, you can also see the pin itself has changed its label. So X is now 1, Y is still 0. And you can see the R pin. Well, I guess it's a little bit harder for you to see But the R pin here now has a label, has a value of 1, but the carry is still 0. So this is telling me 1 plus 0 has a result of 1, but no carry to the next digit. Makes perfect sense, right? Let's flip the bits here. So I flip Y to be on, 1 to be off. Same result. Okay. The output is a 1, and there's no carry. And the last test is to flip both of them on. 1 plus 1 has a result of 0 and a carry of 1. So this sub-circuit is working. Did I miss any cases? Is it possible that I have only tested a subset of all the possible cases? Nope. I have tested 4 cases, and that exhaustively tested every single possible input combination. Great. So this would be a good time to save the file if I were to turn this in, which I'm gonna kind of illustrate to you. So I'm gonna save this file, and you don't want to export it as a bitmap, because I have to be able to run it after you turn it in. So you make sure you save it as a LogicSim project file. Okay. It definitely allows you to save it any place you want to. So I'm going to save it as the into the root folder of this particular user account, and I'll just call that add. Okay. Now this is the magical part. Now that this is working, what you can do is now you can go to project and click add circuit. In other words, you're turning the design of a half adder into a single component. Then you can reuse that component over and over again. Okay. So you can say add circuit, and the circuit name is going to be a half adder because it is only 1/2 of a full adder. Okay. Click that, and it disappears because now it becomes. Oh, I forgot. I have to manually copy and paste it. So I'm going to have to copy this, go to the half adder, and paste it here. So now the half adder, is exactly the same design as what we have in the main window here, except I can now make any number of instances of the half adder. So I don't need it in the main anymore. I can now safely delete it from the main portion of the project. And if I need to make any additional changes, I can still make additional changes in the half adder part, but I don't need to because this is all done already. Are there any questions about what I have just done? No questions? Okay. So if there are no questions about what I have just done, I can now go to this little tab here, and this tab is to it allows you to change how the sub-circuit looks like. Okay. So by default, it looks kind of like this. Okay. It's a very typical diagram for an IC. If I were to make it bigger, it's just basically a rectangle like this with a little notch here. This notch is usually used for the orientation purposes on a chip, on an IC, integrated circuit chip. And most of the time, the pins are usually on the left and right side. But since my pins are to the north and to the south, it kind of copied that design. So when you're in this view, you can make changes if you want to. You can also label all of these things if you want to do that. So what I'll do is I'm going to select this. I can make this rectangle any size. I can make it bigger, smaller, and so on. But if I make it bigger, I have to move the pins as well. So all of these pins, if you select one pin, just kind of observe the lower right-hand side of the screen. As soon as you select the pin, it shows you, whoops, click another key. As soon as you select the pin, it shows you at the lower right-hand corner which pin we have selected in the circuit itself. And you can now move it, anywhere you want, on the screen here. One thing I would do is to label these pins. Unfortunately, there's no quote-unquote automatic tool to label the pins when you're dealing with the look and feel of a subcomponent, of a sub-circuit. So the only thing you can do, unfortunately, which is kind of tedious, is to repeat the labels and use the text tool for labeling purposes. So this is my pin X, and this is my pin Y over here, and this is my carry pin. The relative position of the pins are still the same, so they're still at the same corners of the design. It's just kind of cumbersome to have to create this and just kind of realign everything so that they look about right. There we go. I strongly recommend labeling, the subcircuit, because if you do not label the subcircuit, the input is pretty much symmetric, but the output is not. So that's why it is important to label which one is the carry pin and which one is the result pin. Are we still doing okay so far at this point? Okay, we are just changing how it looks like as a subcircuit, and you can do other fancy stuff too if you want to. Okay, you can put a little, 1/2 of a plus, in the inside to clearly identify this as a half adder. I'm just going to leave it, the way it is at this point. Okay, I lied. I want to label it as a half adder also. Just so that when we design a full adder, it is clear that this is a half adder. Okay. All right, so we are done with a half adder. Now it is time to design a full adder and test it. Okay. So don't turn something into a subcircuit until you have tested it. Otherwise, it may not work, when you put everything together. So to design a full adder, I go back to main here, which is now empty because I have deleted the only circuit design in the main window here. But now I have a half adder, which is kind of cool because this allows you to do something like this. Once you select a half adder, you can now just specify instances of a half adder and specify another instance of a half adder over here. In other words, I turn a half adder into a struct, and now I have two instances of that particular struct in the main design view. Is that okay so far? Okay. Now for a full adder, okay, if we kind of switch back to the note here, for a full adder, the inputs would kind of look like this. So full adder. For a full adder, there are 3 pins as input. Okay, so you have to feed. There's an X and Y as input. There's also a input carry as an input. It has 2 outputs, R as the result as output, and also carry as an output. So there's 1 carry coming in, but there's also 1 carry going out of a full adder. So knowing this, we're gonna do about the same thing as before. We'll have 3 input pins and 2 output pins in this case. So we go back to wiring, go to pin, and I still remember the previous setting. So I'm still specifying output pin facing north. Okay. So there are 2 output pins. 1 facing north is fine. I'm gonna do that. I'm gonna create that one first, which is really just the result, and the result should align with this pin here. The other output pin, I'm gonna put it on the left-hand side. So if I put a pin on the left-hand side of the entire design, the pin itself or the connection point should face east instead. So I'm going to change the orientation or change the connection point so that it faces east. Nope, I made that mistake again. I should have, oh, this is also not C. So this is our result pin. So I want to change the label to R, which is the result of a full adder. But the next pin that I'm creating is going to have the label C, and it's going to face east. And it's going to go, well, I'll just put it here for the time being. I will have 3 input pins. So the 3 input pins, I'll go back to pin here. I'm creating input pins at this point. 2 input pin will face south. The first one has a label of X. It is not an output. If it's not an output, it's automatically an input. So I specify all the properties of the pin, and then I just have to put it here. Okay, this is my first input pin. It is X, and then my next input pin is going to be Y. Everything else being the same, orientation and everything, except the label is going to be Y. So I'm going to put my input pin Y over here. And you can always just readjust things a little bit. The third input pin is the carry from the digit before this one. Okay, so that one I'm going to put it on the right-hand side of the design. If I put an input pin on the right-hand side of the design, that means the connection point has to face west. So I'm going to change the facing here to west. It is still an input pin, so output being no is correct. I don't want to deal with 3-stage. That is good. The label is, oh, I keep doing the same thing. Because I still have this pin selected, so it made the changes to that pin instead of the pin that I'm trying to make now. So I have to go back to here, and then repeat the same thing. I want it to face west, and the label is going to be C. Now, if you don't want it to be just C because there's one C already, we can make this C in, or the input carry. And then we'll put it somewhere around here. And then we can change the other pin to C out, just to be very clear which one is my output carry and which one is my input carry. All right, so I have all the components now for a full adder. Now it is time to make all the connections. Okay, with the connections, the X goes to the X of the first half adder, the Y goes to the Y of the first full adder. So that part is pretty straightforward. Just have to make the connections. Like that. All right, so so that's good. The result of the first half adder goes to one of the inputs of the second half adder. The carry in from the previous digit, I'm going to move this one up a little bit, maybe around here. And this input pin goes to, this doesn't look, it's still correct, it just doesn't look good, okay? So this input pin goes to the other input of the second half adder of this design here, okay? And then the output of the second half adder becomes the actual output of this full adder. This output pin connects to the output pin of the second half adder. Well, no, I take it back. Okay. So let me just do this part here. Okay. I have one single carry out, but I have two output carries from the two half adders. How do I combine the two output carries from the half adders to the output of the full adder? Do an OR, exactly. Okay. So we go back to the logic gates here. Specify a OR gate. It should still have, it's still preserving the settings from before, except this time I can make the gate, face west. So we'll change the orientation to west. 2 input is good. Being narrow is good. So we can now just put it here, like so. And now we just have to draw the connections. So this carry has to go to one input of the OR gate, and then this carry goes to the other output, the other input of the OR gate. The output of the OR gate becomes the actual output of this full adder. So I'm now done with a full adder. Okay, using 2 instances of half adders, I now have a full adder. It's time to test it, right? Just to be sure. To test it, you have to switch the tool, back to here, the little hand, so that you can change the state of the input. If the input carry is a 1, the output is a 1, and then the output carry is a 0. That makes sense. If the input carry is a 0, and we have 1, 1 as one of the inputs, the output is 1 with no carry. That is correct. If we have both of the inputs being 1, the input carry being 0, the output is a 1 and the result is a 0. That is correct. If we have 1 as the carry input and 2 1s as the regular input, the output is a 1. Excuse me, the result is a 1 and so is the carry output. That is also correct. Okay. There are 8 possible cases when you have 3 inputs. So you can basically go through the entire table and make sure that each combination has the right output, in both cases, because we got 2 output pins. but I'm pretty sure this is working correctly. Are there any questions about this design? This is a full adder. So once we have a full adder, we can just make 4 cases or 4 instances of these things to become my basic design for a 4-bit to 4-bit adder. Okay. So I will do exactly the same thing as last time. I'm going to go to project here and add a circuit and add basically my own design as a sub-circuit. So this time I have a full adder. Right? So a full adder by itself has nothing in it because I have everything inside the main window here. So just like last time, I select the entire thing. I usually just do a copy and paste, and when everything is done, then I go back and delete it instead of just doing cut and paste. Because if I do a cut and paste and I forget about something, then I would have lost the design. So I just do a copy and paste here. Make sure it's over here. Then I can go back to the main window and delete this one. Are we still doing okay so far with how to use the software and also what I'm doing with the software? Okay. So now I want to create a 4-bit adder. So I have 4 input from one number, 4 input from the other number, and using 4 full adders in this case. So I go to full adder, and one thing I forgot to do is to change the look of a full adder. So by default, it creates a look like this, which is really, really tiny and difficult to read. So one thing that I personally would like to do is to label the output, make it a little bit bigger, so it's easier for me to see what each input is. So I would just go ahead and make this rectangle. The rectangle, by the way, has no particular meaning. It's really just a documentation kind of thing. Okay, it's really just for documenting the boundary. So the output carry goes here. Okay, that's fine. There's such a thing called an anchor. The anchor is not that important. All it does is to specify when you drag a new design into the main part of the window. The anchor specifies the orientation and also how the design is dragged by your mouse pointer. Okay, so you can basically relocate the anchor all you want, and it doesn't really do a single thing to the logical part of the design. All right, and I'm going to label all of these pins here. So the first pin, I'm still going to label it X, and the second input pin I still label it Y. This is C in, the input, the carry that is serving as the input. This is the result of the full adder, and this is C out. This is the actual output carry. And then I go back and just kind of tediously move things so that they look about right. Yeah, it doesn't really have a zoom feature, so I can't really show you, zoom in what it looks like. But at this point, I'm just really just fixing the design so it looks right. All right. Okay. So now that I have everything looking right, for a full adder, I can now utilize the full adder in my main design again. So I go back to, in your case, make sure you save your design occasionally, okay? This tool is really stable. I have not been able to crash it, but a lot of tools like this kind, because they don't really have a huge user base for testing, they crash often. Okay, it's not unlikely. I have used circuit design tools before, and I'll be spending half an hour to refine a design, and it just crashes. So I have a habit to save every 3 minutes or so, just to be sure that I don't lose anything. Okay, so now that this is all done, I can go back to the main design here. And for the main design, I just need a lot of pins as input, a lot of pins for output, and 4 of these full adders. So the first thing I'll do is to put 4 full adders into the design first. Okay, and you can see why I align the C in and C out, so that it's just easy to make the connections when they're fully aligned like that. And so I'm gonna put 4 of these things right next to each other. Oh, this one is not aligned correctly. Is it? No, the last one is not. No wonder it looks off. There we go. All right, so with a 4-bit adder, you have 4 bits from the first number, 4 bits from the second number, 4 bits as the output, and 1 extra carry as the output. Okay, so we'll go ahead and create all of those pins, but at this point it's just chore. Okay, at this point it's really just chore, because for the input pins we want them to be facing south, not output, 1 data bit, no 3 tri-state, and it's just a matter of changing the labels. Okay, in the homework assignment I specifically asked the labels to be A3 to A0, so that's what we'll do here. So I deal with all the A pins first. So we'll have 4 A pins, 1, 2, 4 here. So these are the pins corresponding to the first number, which is A in this case. And when I go back to here, I can change the label to B, to basically for the other input. So we have B. You can always make this a little bit, make it look a little bit different, but I'm just gonna do a really quick job here. Okay. Now we can go back to each one, to label. This one is A3. This one is A2, this is A1, and this is A0. The number or the digit is designating which bit of the number we're dealing with. And by convention, we put the least significant bit on the right-hand side, and that's why you see A0 all the way to the right-hand side, and A3, which is bit 3 of a 4-bit number, all the way to the left-hand side. And we always count from 0. Okay, it's always bit 0, bit 1, bit 2, bit 3, not bit 1, bit 2, bit 3, and so on. Okay. And I really should do the same thing with B, but it's kind of tedious. I'm not going to waste my time doing that. At least not when I'm just illustrating what to do. Now we can deal with the output bits. The output bits, I'm going to specify those are outputs, and for the label I can just name everything as R. And I want them to be facing north. Okay, the connection point is going to face north, like that. And there'll be 4 of these things. So the first one goes here. Second one goes here. Third one. Fourth one. And I'm actually forgetting another output pin, which is the carry out. So the last carry is also an output pin, but it is the output carry of the entire 4-bit adder. And that one I wanted to face east because it's going to be over here. And that's going to be a 0 coming into here. A 0 is not a pin because it is a fixed value. So for a fixed value, you can go to this one constant here, and we want it to face west in this case. And you change the value, it is the number of data bits is still 1, but you want to change the value to just 0. So once you have that value, you can just kind of stick it over here. And now all that is left to do is to make the connections between the pins. So now I can just go ahead and connect the pins. If you align the components, correctly the first time, making connections of the pins is easy because they should all align like this. And you can see the simulator is actually running right when we make the connections. But this is an error because not all the input pins have been specified yet for that component. So this 0 goes here, and this just doesn't look right. I'm gonna. Sorry, I'm a little picky here. Because otherwise they don't align right. In case you haven't noticed, I'm having a lot of fun here. All right, so we got, see, this one is all done. Input is 0, 0, and 0. The output is a 0. So the output of this one goes here, and you can see right away this one changes to a 0 too. And we are now propagating the 0 all the way through, and we're done. with a 4-bit by 4-bit adder. The only thing left to do is to change the labels. So this is B0, this is B1, B2, and B3. Cool. And you can label the R bits too, R0 to R3. Okay, so now we want to test it, right? I mean, just because we got, the half adder done correctly, the full adder done correctly, it's not, enough, reason to believe that this overall design is working. So we want to kind of come up with a 4-bit by 4-bit adding and make sure the design is actually working correctly. Okay, so what do you guys want to do? Which number adding to which number?
2 plus 5.
2 plus 5. Okay, so we want to do 2 plus 5. So let me just put it here. 2 is 0, 0, 1, 0. 5 is 0, 1, 0, 1. And the result should be 0, 1, 1, 1, which is 7. Okay, so we want to see, this one is too easy, there's no carry. But we'll go ahead and give it a try.
Baby steps.
And since addition is symmetric, it doesn't matter which one is A, which one is B, but just for the purpose of this demonstration, I'm going to say, A is 2, B is 3, B is 5. So A is 2, so it will specify, turn it to the tool here. This is specifying 2, and then B is 5. So this has to be a 1, that has to be a 1. So the output is 0, 1, 1, 1, which is correct. And then the carry out of the entire thing is also a 0 because we don't have an overall carry from a 4-bit addition. Very good. Now, if for those of you who are kind of more into electrical engineering or computer engineering, you can even hook up these outputs. But do it in your own design. Not the one that you're turning in. You can also put those into output components. It has a 7-segment display, a hex display, and so on and so forth. So instead of just outputting, these pins, you can also use LEDs, so they would just kind of light up or not light up. You can have a lot of fun with this. I mean, I'm not gonna use too much class time to do it, but there's a lot of stuff you can do with this one. Any questions about this? Yeah, go ahead. Sorry? That has to be a 0 because there's no. Say again? Constant. When you look at wiring, one option is called a constant. That's the tool that I used. Yep.
When we do the homework, do you want everything to be labeled?
For the final design, yes. I want the input to be labeled, and the output, it's kind of implied, so that one does not have to be labeled. So R3 to R0, they don't need to be labeled, but the input, they have to be labeled.
And then also the Y and C out and C in the R and stuff? Boxes?
No, that one is for your documentation purposes. You don't have to label those. But A and B must be labeled because for subtraction, it's not symmetric. It's not, how is it called? Commutative. So, and as a result, I have to know which one is A and which one is B when I test. Yep. Any questions about the 4-bit adder that I have designed here? No questions? Okay. And if you click on simulate, it also gives you more options. The default works really well. The default gives you simulation is always enabled, even when you're designing the circuit, it's emulating or simulating at all the time. You can make it so that it takes only once so you can basically look at how the signal is propagated, look at the propagational delay and stuff like that, which is kind of fun too. You can also go to logging because it can create a file with the signal changes of all the pins, which can be useful later on if you want to plot it out and look at the propagational delay and stuff like that. So there are a lot of fun stuff you can do with this tool. Even after you get out of this class, if you go to a logic design class, it has specific tools for that as well. Okay, so you can specify the truth table and then leave it up to this tool to figure out what type of gate configuration can implement the truth table that you have specified, which is really kind of neat. Nah, you guys don't think it's neat. Okay. So that's it for your homework assignment. I mean, this I have done, the equivalence of your homework assignment, but using, adders instead of subtractors. So switching back to the homework description here. So for your homework, it is called a 4-bit subtractor. And what you have to do is to do pretty much the same thing, except yours is going to be a subtractor instead of an adder. So there are certain limitations to how you can do your homework assignment. Okay, so your homework assignment is to use LogicSim, which is the software that I was just using a little bit ago, to build a 4-bit subtractor. Observe the following specifications. You have to name the design and the file name, subtractor. Use the default extension, but name it subtractor. You can only use AND gates, OR gates, and NOT gates. Other than the pins, those are the only gates you can use. And the reason why I have to specify this is a subtractor is one of the components. I don't want you guys just to use a subtractor component, specify 4 input, and then you're done, right? I mean, there's nothing else to do. So you have to start from scratch and use only the basic logic gates for your design. Definitely use pins. Okay, remember to designate some of those as output, some of those as input, but you want to disable the tri-state or the 3-state option of all the pins. I strongly recommend that you use a nested design like what I did. Otherwise, there will be a lot of copying and pasting, which is really, really awful for something like this. Your final design, has to have the following input-output. Use the label property of a pin to label it. Okay. Use a text label to label pins of a component. You need 4 input pins designated A3 to A0 for the first number. 4 input pins for the second number, B3 down to B0. 4 pins for the output. So I did specify the output. They also have to be labeled D3 to D0 in this case for the difference. The difference has to be A minus B. Okay? Because subtraction is not commutative, so I have to specify you are subtracting B from A. Okay? And you also have one output pin designated as C as the final borrow flag, or the borrow bit. The reason why I don't use B as the borrow bit has to do with the convention of a computer. So inside an Intel processor, or when we are dealing with the instructions, the carry bit and the borrow bit are really the same thing. Okay? But most commonly, it is referred to as the carry bit, not as the borrow bit, even though it does serve the function of a borrow bit in this case. So I do suggest that you use a nested design because it just makes everything easier when you use a nested design. Design a half subtractor first, test it. If it works, turn it into a component or sub-circuit as the tool says. And then you design a full subtractor using 2 half subtractors. Test it, make sure it works. If that works, use 4 instances of those, in your final design, and you should be able to get this done, not using a whole lot of time. I mean, I was, explaining, the whole time, and it took me about maybe 45, 50 minutes to get it done. And the tool, as I said, is surprisingly easy to use. I have used a lot of tools like these, logic design, circuit design, and stuff like that. And many of those tools will take me at least a few days just to get used to the user, interface. And then I can actually get down to the design itself. This tool, I was comfortable with it within minutes. It was, so intuitive to use compared to the other tools. LogicSim also comes with a really good tutorial and help. It's built into the tool itself. So make use of that if you need to. And also plus the lecture recording, because everything that I'm doing today is fully recorded. The only thing that you may not be able to tell just watching the recording is what I'm doing on the keyboard and the mouse. Okay, am I right-clicking? There's no right-clicking. I mean, I was not right-clicking at all. So there's just click and drag for the most part, of what we did, what I did today. So for your reference, for subtraction, we have 4 cases also. 0 minus 0 has a result of 0 and a carry of 0, or carry is actually borrowed in this case. 0 minus 1 has a result of 1 and a borrow of 1. 1 minus 0 has a result of 1 and no borrow. 1 minus 1 has a result of 0 and no borrow. Those are the 4 cases. But you will have to come up with your gate design, the only part that is really even challenging is the borrow flag, because the rest is pretty much the same as an adder. All right. Any questions about your homework assignment? It's a file submission. You just have to turn in that one single file for the simulator, project. That's all that you have to turn in. Are there any questions about this? Yep.
When is this due?
It's due in a week, so next Thursday is the due date. So I typically give you guys like 2 class meetings before the assignment is due. So if you start early, if you start to do it in the lab like today, that's a really good head start, because you just have a lot of time, to ask questions if you run into any type of problems. But if you just work on it over the weekend, you still have next Tuesday to ask questions. So there's plenty of time for you guys to get started, ask questions, and get used to the tool. Right? Any other questions? Yep.
For extra help, is there a computer lab or something like that we can go to? Kind of like Sac City has one.
I don't think there's anyone who can help you with the software itself.
Right.
But to use the software, it's just a Java file. You can just download the Java file, stick it onto your thumb drive, or you can re-download from their website, every single time. That's,
Oh, I mean like a computer lab that's open all the time. Like Sac City has one that's open like 9.
Room 152 usually has at least one open section.
Okay.
So you can go to room 152. Do you know where that is?
Yeah.
Yeah. So you can go there, to work on your homework assignment.
Okay.
Yep. This tool only requires Java. And all of the computers here, have Java installed already, so you should be okay. Even the library may be okay too, because you just have to download the tool itself on the fly. Double click on it to start up the tool, and even if you don't have anything to save your design, you can work on it. When you're done, make sure you save it and then email that to yourself as an attachment. All right. Any questions? Any other questions about this particular homework? No questions? Okay. I just want to show you what else, what other components are available in this tool. And I know it's a little bit beyond the scope of this class, but if you look at all the different gates, it has NAND gates, NOR gates, and so on and so forth. Those gates are important because when you're actually doing design in semiconductor, a lot of those gates are native to the hardware design, because a regular OR gate and a regular AND gate is actually not native to the design of a circuit board. It also has multiplexers, so you can have multiplexers and demultiplexers, decoders. These are very, very useful and important components inside the processor. When you look at arithmetic, and this is why I don't want you guys to use a subtractor, because you can actually pull a subtractor and say, I only needed to work on 4 bits, and you're done with your homework. Well, you still have to splice the output into pins and stuff like that, but you don't have to go through the design of the circuit. So that's why I specifically ask that you use AND, OR, and NOT gates, in your design. Okay, you cannot use, this particular library part. Yep.
What is the 100% on the corner represent?
Ooh, that's my zoom tool. You got it. Good one. That's a good one. Now we know where the zoom is. Very good. I'm not going to redo the whole thing, with zoom in. We have multiplier, dividers, and so on and so forth. But with all of these components, you can actually design a very simple processor Okay, you can actually implement a small, tiny little processor with registers, a memory bus, and stuff like that, using these basic components. So this is a really, really cool tool because you can actually put together a tiny little design that has memory, CPU, simple input-output, and stuff like that. Which is kind of way beyond the scope of this class. This is basically where we stop, in terms of designing something, circuit-wise. But for those of you who are interested, you can push this tool a lot more than what we are using it for this assignment. Right. Any questions about this? No questions? All right. So if there are no questions, I'm going to leave it here. I'm not going to close this window just yet. But I'm going back to the notes here and basically just move on and continue with topic 1. All right, so last time we talked about binary numbers, addition and subtraction. So let me just open this one as a new tab. There's a link here. And that's basically the stuff that we talked about already, what is number representation, how to deal with binary numbers. We talked about base conversion last time, so all of this stuff, we went over all of this stuff already. We talked about adding, okay, and how to perform adding using just 2 rows. And this is subtraction, okay. I think we did not cover subtraction entirely, but the only special case about subtraction is what is 0 minus 1. Okay, 0 minus 1 has a result of 1 and a borrow of 1. Okay, that's the only kind of more special case of subtraction. We talked about 2's complement. Okay, on Tuesday we talked about 2's complement. 2's complement is not one of the slides here. It is actually talked about a little bit later in another slide. Let me go back to my notes here and pop up the next one. Half adding and full adding. Okay, that one talks about adding, how you can specify a full adder using 2 half adders and what components are inside of 1 half adder. Okay, nothing new. It's stuff that we talked about already. So we talked about what is a full adder. This is a truth table, by the way, of the input pins. 0, X, and Y are the input pins. R and C are the output pins. And the tool that we are dealing with, LogicSim, can take a truth table and then come up with the design to implement the output of a truth table. So that is a really, really useful tool because a lot of times you know what the output is supposed to look like when the input looks like this, but you don't necessarily want to spend the time to figure out what kind of gate combination will make that happen. So the tool that we were just using earlier today actually has the ability to figure that out. Well, for simple cases anyway. So this we talked about already. A full adder is made out of 2 half adders. And that's about, I use these, kind of obscure way to describe stuff, but for the most part, it's really just saying that the carry flag of 1 full adder becomes the input carry of the next full adder, and so on. It's basically just saying, how the carry flag is propagated. And how to make use of explicit carry flag and implicit carry flag. So this one is kind of interesting because if you do not use the carry flag, just propagate it from the previous adder, you end up with pretty complicated equations. Okay, we talked about it the other day too. Remember, I kind of copied and pasted, stuff, and ended up with a fairly big equation. That's basically what that is. Okay. All right. And optimizing a full adder for 2 bits, it looks like this. Okay. So if you're adding 2 bits to a 2-bit number to a 2-bit number, you end up with 4 inputs, okay? X0, X1 is the first number, Y0, Y1 is the second number. The result is you have 2 bits for the sum, okay, so that's S0 and S1, and then 2 output carries, which is C1 and C0. So this is the truth table of the entire 2-bit adder. And to make it simple, okay, you can optimize this into a form that looks like this. So for 0, 0 as the input, and 0, 0 as the output, oops, I take it back. For x1, y1 being 0, and x0, y0 being 0, the output is 0 for the sum bit. You don't have to worry about this. I'm not going to ask any questions about k-maps, but this is a mechanism, or this is a method where you can look at a truth table of something, and then in return, come back with the simplest equation using logical operations to implement the truth table. Okay, so skipping all of these, kind of intermediate steps, the final result is the carry C1 or the carry flag out of the second adder can be expressed as this equation here. For those of you who are into computer engineering and electrical engineering, you will see K-map again. Okay, there's no way around K-maps, and what this slide is really just getting into. Okay, for computer science people, I don't think you will see much of this anymore. How many people in this class are going into a computer engineering or electrical engineering program? 3, 4. Okay, so the rest are in software, computer science. Okay. I wish I took more classes in computer engineering because that's actually in many ways fascinating as well.
It's not too late. You still take classes.
Yeah, especially if my kids decide not to go to college, then I have to use that use their 529 fund for my education. I've been threatening them since first grade. If you're not going to college, I'm going to use your money and get my second degree, third, fourth, or whatever. All right, so we are pretty much done with adding and subtracting. Are there any questions about adding and subtracting? I haven't talked about the third slide on adding and subtracting, which is this one here. Things are a little bit fragmented, because I tend to write something a little bit newer. When I see the old one is that's kind of dated, I would go look at it in a different way. But basically, it goes over the same stuff. Okay. Revisiting the add rules, 1 + 1 is 0 with a 1 as a carry, that sort of thing. Bit operators, and, or, and not. Half adding and full adding, same stuff that we have been talking about, it's just presented maybe a little bit differently. But then they also talked about signed numbers, okay, which is something that is kind of unique to this particular document, is, what about signed numbers? Because in C++, you have signed integers versus unsigned integers. So the question now is, how do we deal with those numbers? And the answer is, for the most part, you don't. Okay? For the most part, there's no difference between adding signed numbers versus unsigned numbers. Okay? The only time signed versus unsigned has any difference is when you compare. Okay, well, okay, and also multiplication and division, but not considering multiplication and division, signed, whether a number is signed or not, it's only important when you compare. Okay, I illustrated the difference on Tuesday. Why in comparison, you really need to know whether to interpret a bit pattern as signed or unsigned. But for everything else, it's not really that important. Okay, so this is really just covering all the stuff that we talked about on Tuesday. So I'm just going to go over this a little bit. 2's complement is basically 1's complement, also known as bit naught, or the inversion of bits, plus 1. Okay, so we kind of talked about this on Tuesday, except we were dealing with 4-bit numbers instead of 8-bit numbers. All of these examples make use of 8-bit numbers. So for the most part, it's just wider and has more bits. And here's a 4-bit number example. Okay. So are there any questions about 2's complement. Well, let's just go through a few more examples with 2's complement as a way to invert a number, okay, to get to the negation of a certain value. So I'm not 100% sure that I covered all of the cases of using 2's complement. Let's figure out what is 5 minus 7. Okay, 5 minus 7. How difficult can that be, right? It's -2. Okay, that's a perfect answer. Can we do this in binary? That's the question. Okay, can we do a subtraction of 5 minus 7 and come up with the representation of -2 in binary using only things that we have talked about so far? Okay. We can always do a subtraction, but let's not do that. So instead, what we'll do is we'll say, this should be the same thing as 5 plus the negation of 7, and we should still end up with -2. Is that making any sense? Okay. So what we want to do is to find out how is -7 represented as a 4-bit number. That's the first thing we want to do. Well, we know 2's complement is the same thing as negation, so the 2's complement of the bit pattern representing 7 should represent -7. 7 is 0, 1, 1, 1 as a 4-bit number. 2's complement is the same thing as 1's complement, which is bitwise not, applied to the same bit pattern, plus 1. So that becomes 1, 0, 0, 0 as a binary number, plus 1. And the result is 1, 0, 0, 1. So what this means is 1, 0, 0, 1 as a 4-bit pattern, as a signed number, is representing -7 as a value, as a quantity. Are we doing okay so far with this part here? Okay? No? Okay. 0, 1, 1, 1 is representing +7. Is that okay? Because it's 1 plus 2 plus 4. Okay. But I claim that 2's complement, which is represented by C2 here, okay, 2's complement is the same thing as arithmetic negation. So that means if I apply 2's complement to the bit pattern representing +7, whatever comes out of 2's complement should be the representation of -7. Is that okay?
Yeah, that makes sense.
Okay. So 2's complement is 1's complement, which is just bitwise not plus 1. The bitwise not of 0, 1, 1, 1 is 1, 0, 0, because we just flip all the zeros to 1s and all the 1s to 0s. And so we end up with a bit pattern of 1, 0, 0, 1, and which should represent -7 as a quantity. So now the question is, if I have 0, 1, 0, 1, which is 5, plus 1, 0, 0, 1, which I claim is the representation of -7, I should end up with the representation of -2. Are we doing okay so far with this? Okay. So let's go ahead and perform this addition here. I'll do the same thing as usual. This has a result of 0, and the carry from before is always a 0 because this is the least significant bit already. 0 plus 0 is, I have to put a 0 here, okay, because this 0 is due to this 0 plus this 0. There is 1 carry from this 1 adding to this 1. Okay? This 0 plus this 0 is a 0. This 0 plus this 1 is a 1. And neither gave me a carry, so this carry is going to be a 0 because it's an OR of the carry of both of those additions. 1 plus a 0 is a 1. 1 plus a 0 is a 1. And I do not have a carry, so this carry is going to be a 0. 0 plus 1 is a 1. 1 plus 0 is a 1, and end up with no carry as an overall addition. So 1110 is the answer. The big question is, does 1110 represent -2? Is this in fact representing -2? So how can I look at a number with the most significant bit being a 1, which means it's representing some kind of negative value, but how do I know the magnitude of this negative number? I can apply 2's complement again. right? Knowing that 1110 as a 4-bit number is representing a negative quantity, if I take the 2's complement of 1110, I'm just flipping the sign. So I should get the magnitude of this negative number, or the absolute number of this negative number. Is that making any sense? Okay. So let's go ahead and do that. Okay. So if I apply 2's complement to 1110, it is the same thing as negation. Knowing this is already a negative number, this should give me back a positive number, which is the quantity, which is the magnitude of the negative number. All right. So 1's complement is bitwise not, which means all the 1's become zeros, and that 1 single 0 becomes a 1. It's exactly 2. Okay? So everything that we talked about so far, they all work together. 2's complement as a way to do negation works really, really well with the rules of adding and subtracting, which is great because it greatly simplifies the processor design. We don't have special circuits just to deal with signed numbers. It's the same way as dealing with unsigned numbers. Okay. Are there any questions at this point? How everything connects, addition, subtraction, how we use gates, and, or, and not to implement subtraction and addition, and what is 2's complement, and how 2's complement is being used to represent negative numbers or negative quantities. With this class, it's not about the memorization. Okay, the rules of addition and subtraction is simple. Okay, the equations are fairly simple too. It is about how everything connects. Okay, so what you need to do is to draw the connection between all the concepts that we have talked about so far. That is the one single most important thing that you have to do that I cannot do for you. So studying for this class is maybe a little bit different from studying for, say, history or some of your other classes where you have to remember things. But in this class, it's not about memorizing things. It's about making the connections. All right, well, we are running out of time for today. You have your homework assignment. I will be in room 128 for those of you who want to get a head start for the homework assignment. And the lecture recording will be online soon enough.
You should pass out the attendance sheet again.
Huh?
You should pass out the